two earthquakes shook California within days. Normally, that wouldn't alarm scientists. California experiences thousands of earthquakes every year, and most are considered part of the state's ongoing tectonic activity. But this time, something was different. These earthquakes occurred just as researchers announced an unexpected discovery beneath California's most dangerous fault junction, A. Discovery that is forcing scientists to rethink how stress may be moving deep beneath one of North America's most complex seismic regions. At first glance, these seem like two completely separate stories. One is about a handful of moderate earthquakes that briefly rattled parts of California. The other is about a scientific study examining structures buried miles beneath the Earth's surface. Yet, when those two stories unfolded almost simultaneously, geologists didn't simply focus on the shaking itself. Instead, many began asking a much larger question. Could this new discovery change how scientists understand earthquake hazards in California? That question matters because millions of people live within reach of California's active fault systems. Every time the ground shakes, public attention immediately turns to one familiar concern. Is this the beginning of the big one? It's a reasonable question, especially in a state where devastating earthquakes have shaped both its landscape and its history. But here's the first important fact. The recent earthquakes do not prove that a major earthquake is about to happen. And the newly published research doesn't claim that they do. Instead, what scientists have found is something arguably more important in the long run. Rather than predicting the next earthquake, the discovery could improve our understanding of how seismic stress travels beneath one of the most complicated tectonic intersections on Earth. That distinction may sound subtle, but it completely changes how this story should be understood. By the end of this video, you'll understand what scientists actually discovered beneath the Mendocino Triple Junction, why the recent earthquakes have drawn renewed scientific attention, and why separating established evidence from speculation is more important than ever. So let's begin with what actually happened. Within just a few days, multiple moderate earthquakes were recorded in California, including events that quickly spread across news outlets and social media. While their magnitudes were far below those associated with California's most destructive earthquakes, they were strong enough to remind residents that the state's fault systems are constantly active. For many people, the timing alone was enough to reignite fears that something much larger might be unfolding beneath the surface. Scientists, however, approached the situation very differently. Their first questions weren't whether a larger earthquake was coming. Instead, they asked where these earthquakes occurred, which fault systems were involved, whether the events were isolated or part of a broader sequence, and whether they revealed anything new about how stress was being redistributed through California's crust. Those questions are critical because earthquakes are rarely studied as isolated events. Every earthquake, regardless of its size, provides another piece of data. Sometimes that data confirms existing models. Occasionally, it challenges them. And in rare cases, it points researchers towards something they hadn't recognized before. That's exactly what makes this story so unusual. Even before these recent earthquakes captured public attention, another team of scientists had been investigating thousands of tiny seismic signals beneath Northern California, signals so small that no one on the surface could feel them. Hidden within those nearly invisible earthquakes was evidence suggesting that the underground structure beneath the Mendocino Triple Junction may be far more complicated than scientists previously believed. That doesn't mean researchers have discovered a hidden fault capable of triggering the next catastrophic earthquake. It doesn't mean California is suddenly entering a period of greater danger. And it certainly doesn't mean anyone has learned how to predict earthquakes. What it does mean is that one of the most important tectonic regions in North America may not work exactly the way earlier geological models suggested. And if our picture of the underground architecture changes, our understanding of earthquake hazards may change with it. That brings us to the heart of today's story. To understand why this new discovery matters and why scientists are treating it so seriously, we first need to understand what makes the Mendocino Triple Junction unlike almost anywhere else on Earth. Once you see how three massive tectonic plates collide, slide, and interact beneath Northern California, you'll understand why even a subtle discovery beneath the surface can reshape decades of scientific thinking. To understand why this latest discovery has generated so much attention, we first need to answer a simple question. Why here? After all, California is home to hundreds of active faults. Earthquakes occur somewhere across the state almost every day. So why are scientists focusing on one remote region along Northern California's coastline? The answer begins with the Mendocino Triple Junction. Unlike the famous San Andreas Fault, which is essentially a boundary between two tectonic plates, the Mendocino Triple Junction is where three massive tectonic plates meet the Pacific Plate, the North American Plate, and the Gorda Plate. Each plate is moving in a different direction. The Pacific Plate slowly slides northwest. The North American Plate moves southwest relative to the Pacific Plate. Meanwhile, the oceanic Gorda Plate is being forced beneath North America in a process known as subduction. Imagine three enormous conveyor belts pushing, pulling, and grinding against one another 24 hours a day, every day, for millions of years. That constant motion never stops. The rocks don't suddenly decide to move during an earthquake. They are always moving. An earthquake simply marks the moment when decades, or sometimes centuries, of accumulated stress are released in just a few seconds. That's why scientists don't view earthquakes as isolated events. Instead, they see them as brief snapshots of a much larger geological process that has been unfolding for millions of years. And nowhere is that process more complicated than beneath the Mendocino Triple Junction. This is also why the recent California earthquakes attracted more scientific attention than their magnitudes alone would normally justify. A magnitude 4 earthquake isn't unusual for California. By itself, it doesn't tell scientists that a larger earthquake is becoming more likely. But when earthquakes occur in or near one of the world's most complex tectonic environments, researchers immediately begin asking a different question. Is this simply routine seismic activity, or is it revealing something about how stress is moving through the fault system? That distinction is critical. One of the biggest misconceptions about earthquakes is that stress builds along a single fault until it finally snaps. Reality is much more complicated. Think of a spider's web. If you pull on one strand, the entire web responds. Some sections tighten, others relax. The same idea applies beneath California. When one fault slips, it can slightly increase stress on neighboring faults while reducing stress elsewhere. Scientists call this process stress transfer, and understanding it has become one of the central goals of modern seismology. The challenge is that stress transfer depends entirely on knowing what the underground structure actually looks like. If parts of that structure are missing from geological models, then calculations of how stress moves through the region may also be incomplete. That's exactly where the new research enters the story. For decades, scientists believed they had a reasonably accurate picture of the deep tectonic architecture beneath the Mendocino Triple Junction. Then researchers began studying something most people have never heard of. They're usually far too weak for people to feel, yet they provide an extraordinary window into what's happening deep underground. Instead of focusing on the large earthquakes that make headlines, researchers analyzed thousands of these tiny seismic signals. What they found surprised them. Rather than fitting neatly into existing geological models, the signals pointed toward evidence of a previously unrecognized underground structure, a captured slab fragment buried beneath the Triple Junction. That discovery doesn't mean scientists have found a hidden fault that's about to trigger California's next catastrophic earthquake. Instead, it suggests something arguably more important. Our underground map may have been incomplete, and if the map changes, our understanding of how tectonic stress is distributed may also change. History has shown that even small improvements in geological models can reshape earthquake hazard assessments for decades. But before drawing any conclusions, scientists still had to answer one crucial question. Does this remarkable discovery actually change earthquake risk, or does it simply improve our understanding of how the Earth's crust behaves? That's where the scientific debate begins, and where the evidence becomes even more fascinating. That question brings us to the most important part of this story. What exactly did scientists discover? And how much does it actually change? Whenever a new earthquake study makes headlines, two opposite reactions usually appear almost immediately. One group assumes scientists have uncovered evidence that California is moving closer to the big one. The other argues that it's just another scientific paper that won't change anything. Interestingly, neither conclusion reflects what the research actually says. Let's begin with the strongest argument from those who believe this discovery is significant. If scientists have identified a previously unknown underground structure beneath one of North America's most active tectonic regions, then every existing seismic hazard model built on older geological maps deserves another look. Earthquake models are only as accurate as the information they're based on. A more complete picture of the Earth's interior can lead to more accurate estimates of how stress travels through fault systems over long periods. That's why researchers are excited, not because they believe they've found the source of California's next catastrophic earthquake, but because they've found evidence that the underground architecture may be more complicated than previously understood. That is an important scientific distinction. Now, let's look at the other side. Does this discovery mean the recent California earthquakes were caused by this newly identified structure? Right now, there is no evidence supporting that conclusion. The recent magnitude 4 earthquakes are real observations. The newly identified slab fragment is also supported by the research. But connecting those two events into a direct cause and effect relationship would go beyond the available evidence. This is exactly where responsible science becomes different from speculation. Researchers constantly ask difficult questions. Could these underground structures influence stress transfer? Possibly. Could they affect future seismic hazard assessments? Very likely. Can they explain every recent earthquake across California? Not based on today's evidence. That's why scientists separate hazard assessment from earthquake prediction. Those two ideas are often confused, but they're fundamentally different. Hazard assessment asks a long-term question. Which regions are most likely to experience damaging earthquakes over years or decades? Earthquake prediction asks a much harder question. Exactly when will the next major earthquake happen? Modern science has become remarkably good at answering the first question. The second remains one of geology's greatest unsolved challenges. That doesn't mean earthquake science has failed. In fact, the opposite is true. Today's researchers can map faults with extraordinary precision. They can monitor ground deformation using GPS satellites. They can detect tiny, low-frequency earthquakes that previous generations of instruments couldn't even record. They can model stress transfer across complicated fault systems using powerful computers. And with every improvement, hazard maps become more accurate. Communities gain better building codes. Engineers design stronger infrastructure. Emergency planners develop more realistic response strategies. Those advances save lives even without predicting a single earthquake. That's why the Mendocino Triple Junction study matters. Its greatest contribution isn't that it predicts disaster. Its greatest contribution is that it gives scientists a better blueprint of one of Earth's most complicated tectonic intersections. Better observations produce better models produce better hazard assessments, and better hazard assessments ultimately produce safer communities. So where does the scientific community stand today? The current consensus is remarkably consistent. Researchers agree that the Mendocino Triple Junction remains one of the most active and complex tectonic environments in North America. They agree that the newly identified underground structure provides valuable new information about how this region evolved over millions of years. They also agree that these findings should be incorporated into future geological and seismic hazard models. Where debate still exists is over how much this hidden structure influences the movement of tectonic stress today. Answering that question will require years of additional monitoring, independent studies, and future earthquakes that either support or challenge the new model. That's how science moves forward, not through one spectacular discovery, but through repeated testing, independent verification, and continuous refinement. Which brings us to the final and perhaps most important question. If scientists now understand this region better than ever before, what does that actually mean for the millions of people who live across California today? By now, it's probably clear that this story was never just about 2 moderate earthquakes. Yes, those earthquakes captured public attention. Yes, they reminded millions of Californians that they live in one of the world's most active seismic regions. But the real story lies much deeper, literally beneath our feet. The recent earthquakes happened to arrive at a moment when scientists were already uncovering new evidence beneath the Mendocino Triple Junction. That timing naturally sparked questions about whether the two were connected. So what does the evidence actually tell us? First, here's what scientists know with a high degree of confidence. California will continue producing earthquakes. That's not a prediction. It's an unavoidable consequence of three enormous tectonic plates that continue moving every single day. Whether anyone feels them or not, stress is constantly building, shifting, and occasionally releasing along hundreds of active faults throughout the state. Scientists also know that the Mendocino Triple Junction remains one of the most geologically complex places on Earth. The interaction between the Pacific Plate, the North American Plate, and the Gorda Plate creates an environment unlike almost anywhere else in North America. Every new dataset collected from this region helps researchers better understand how these enormous geological forces interact over decades, centuries, and even millions of years. They also know something else. The newly discovered underground structure is real evidence, not speculation. Using thousands of low-frequency earthquakes, researchers identified features that earlier geological models had not fully recognized. That discovery doesn't rewrite everything scientists thought they knew about California. But it does improve the map. And in earth science, a better map often leads to better science. Now let's look at what scientists don't know. They cannot say that this hidden structure caused the recent earthquakes. They cannot say the recent earthquake sequence means California is entering a period of increased seismic danger. Most importantly, they cannot predict when the next magnitude 7 or magnitude 8 earthquake will occur. That uncertainty sometimes frustrates people. After all, weather forecasts continue improving every year, so why can't earthquakes be predicted the same way? The answer is that the Earth doesn't behave like the atmosphere. Storms can be observed directly as they develop. Scientists can watch clouds form, measure temperature changes, track wind patterns, and monitor hurricanes from satellites in real time. Earthquakes are completely different. The processes responsible for them occur miles beneath the surface, hidden inside solid rock where direct observation is almost impossible. Researchers must reconstruct what's happening using seismic waves, GPS measurements, underground imaging, laboratory experiments, and increasingly sophisticated computer models. In other words, scientists are solving an enormous puzzle without ever seeing the complete picture. Every earthquake adds another piece. Every research project fills another gap. And every discovery brings that picture into sharper focus. That's why studies like this matter so much. They're not valuable because they create dramatic headlines. They're valuable because they gradually reduce uncertainty. Today's discovery may improve tomorrow's hazard model. Tomorrow's hazard model may influence future building standards. Those stronger buildings may one day protect thousands of lives during a major earthquake. That's how scientific progress works. Not through one breakthrough that suddenly answers every question. Of careful discoveries that slowly improve our understanding of the natural world. So what should Californians actually take away from this story? Not fear. Preparation. The recent earthquakes are a reminder that seismic activity is a normal part of life in California. The new research is a reminder that scientists continue improving our understanding of the forces responsible for that activity. Neither message suggests panic. Both support preparedness. That means maintaining emergency supplies, securing heavy furniture, understanding local evacuation procedures where appropriate, and staying informed through trusted scientific organizations rather than social media rumors or sensational headlines. Because when the next earthquake happens, and eventually it will, the best protection won't come from someone predicting the exact day it occurs. It will come from years of scientific research that improved hazard maps, strengthened infrastructure, advanced earthquake monitoring systems, and helped communities prepare long before the ground began to shake. In many ways, that's the real significance of the discovery beneath the Mendocino Triple Junction. It isn't a warning that disaster is imminent. It's evidence that scientists are still uncovering hidden chapters in the story of how our planet works. Every new observation makes the models a little better. Every better model improves our understanding of seismic hazards. And every improvement gives society another opportunity to prepare more intelligently for the future. So while the recent earthquakes may eventually disappear from the headlines, the questions raised by this discovery will continue driving earthquake research for years to come. Because the most important question isn't whether scientists found evidence that the big one is coming. The more important question is this: how much closer are scientists to understanding one of Earth's most powerful tectonic systems? If you enjoyed this evidence-based analysis, Subscribe for future updates as we continue following the latest earthquake research, geological discoveries, and natural hazards separating scientific evidence from speculation, so you always understand not just what is happening, but why it matters.